This next video is about electrons. I know we've talked about electrons many times, but this is going to be something very specific and definitely more in detail. So when we were talking about atoms and the structure of the atom, the modern atomic structure of the atom, we were talking about Thomson and Rutherford and Soddy, some other people. And I had mentioned Bohr and Heisenberg. And these two guys were the ones that came up with the structure with the location of where the electrons are. So far, we're talking about electrons being in orbit, but we haven't been specific about where those electrons are, or what the word orbit means associated with an association with an electron. So that's what we're going to do. The first person to come up with a plausible model for the atom is Niels Bohr. Bohr ended up winning the Nobel Prize for this, and his model is kind of a planetary model. When we talk about atoms, or you see pictures of atoms, I'll roll down here a sec, it's usually something that looks like this. And this wins him the Nobel Prize. And it can be helpful, but it's not good enough for our purposes. And we'll talk about that why in a bit. Okay, so Bohr has another model, and Heisenberg has another model, where Bohr's model is intuitive because we can picture things rotating around something, especially like planets rotating around the sun or the moon rotating around planet. When we look at Heisenberg's model, it's convoluted at best. I will say that Heisenberg and Bohr worked together. Bohr had already won his Nobel Prize, and Heisenberg approached Bohr to talk about the modeling of where the electrons are located in orbit. And their relationship was collegial. I mean, Bohr had just won the Nobel Prize, and Heisenberg is saying, hey, I think there's something wrong with your model. And Bohr did, point at his Nobel Prize and say, yeah, when you win a Nobel Prize, come talk to me. Heisenberg actually never did win a Nobel Prize. But Heisenberg says this to Bohr, and Bohr is like, you know what, I know there's some stuff that's not correct about the model. It doesn't express all the data that we have. So what do you got? And let's talk about it. So Heisenberg's model, the image is what we have here on the right. This model is based off of calculus and statistics and wave functions. The math associated with this is beyond this class. It's beyond most people. After Heisenberg and Bohr, after Heisenberg convinced Bohr this is what we should be doing, Bohr helped Heisenberg, and he took him around from place to place. It was if you came up with an important concept at this time, the best way for you to disseminate your information was literally to get on a plane or get on a boat or drive a car to another university and talk to the people that were in your field. So that's what they did. They went around from university to university, and they spoke with different people about Heisenberg's model. And here's Bohr, who already won the Nobel Prize for his model, and he's promoting Heisenberg's more complex model. When they got to Princeton, New Jersey, that's where Albert Einstein spent the latter portion of his career. After explaining the model, Einstein said, I think this is it. Sorry, Bohr, but this is definitely better than your model. And this explains a lot more than we can with your model. I can't follow the math. And so this is Albert Einstein explaining that he is unable to follow Heisenberg's math. That is how difficult this math is. I guess 10,000 people, 20,000 people on the planet could do the math with like a regular calculator and a pencil, and a piece of paper. We're okay with it now because we can have computers do the modeling for us. But the actual math is not something that people are going to come up with on their own for the most part. So what's interesting about these two images is they're of the same atom. So they're both lithium. And the way that we would know that they're both lithium is a couple of reasons. One, in the Bohr model of the atom, which is a lot easier to see, there are 3 electrons there. And an atom must have same number of protons as it does electrons to be electrically neutral. And so then we've got 3 electrons. So that means we have 3 protons. So that means we must be talking about lithium. You can also see that there are 7 orbs in the middle there in the nucleus, and 3 of them are red and 2 of them are, or 4 of them are blue. And that's the normal atomic mass of lithium, a mass of 7. On the table it says 6.9, blah, 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 something or other, but it's 7 for the highest concentration isotope. And so that gives us 3 protons and 4 neutrons. Okay, the model on the left is also lithium. It's a little harder to see, but the nucleus is the same. There's 3 protons and 4 neutrons. But it seems like we got a heck of a lot more electrons than just 3. So I'm not sure if I'm dating myself, but transparencies. Do we know what a transparency projector is? Let me pull this up. This is my best analogy for this. All right, so let's see. Click on this guy, and then open image in new tab. There we go. Here's a transparency projector. That's too big for that screen. So you put a piece of clear transparency film on here, and then you write on it, and then it's reflected up onto a screen. And this is how people did it when I was in middle school. Chalk before that, but so they'd have dry erase markers, or what to pass for dry erase markers, erasable markers, and you draw it. So what Heisenberg did is he started a calculation for, we'll use lithium in this case, started a calculation for lithium, and he said, what would happen if I had these 3 electrons that were moving around, and they had to obey certain laws, and the nucleus had a certain amount of pulling power. Okay, and so he did the calculation, and with wave function calculations, you can get different answers by allowing them to try do more and more calculations with that. So what he did is he did his calculations, then he stopped, and then he put 3 dots on a piece of transparency paper. Then he started the calculation over, and then he stopped, and he took another transparency paper and he put 3 dots down, and then he laid it over the top of the first. So what you're really looking at is Heisenberg doing the calculation hundreds of times and then laying his results over the top of each other each time. So this is the same 3 electrons over and over again. And what you can see is there's a higher density of electrons in the middle here and less density of electrons on the outside. So what Heisenberg's model is doing is showing basically a cloud of where you should be expecting to find the electrons. And you can find the first 2 electrons in that denser cloud, and then the 3rd electron in a less dense cloud. It's less dense for 2 reasons. 1, there's only 1 electron instead of 2 electrons. But 2, it's also a lot more space to take up, a lot more volume for that 1 electron to be occupying. So you're not seeing the dots as closely together. In the inside, you can see that those things are constantly being stacked on top of each other. So Heisenberg's model, again, is a calculation, a predictable calculation of where he is predicting these electrons are going to be found, given the fact that there are 3 electrons in a nucleus, and they have certain properties like the electrons are opposed to each other, the protons and the electrons are attracted to each other. And putting that into his model, he came up with this idea. A side note here, it's kind of interesting about Bohr is Bohr had to flee persecution from the Nazis. So he left Denmark, left his lab in Copenhagen, and he knew he couldn't take his Nobel Prize with him. It's mostly gold. He was assuming he would be robbed or it would be lost or whatnot. So instead of risking that, he took his gold Nobel Prize medal and he put it in aqua regis, which is Latin for royal water, and that's a combination of hydrochloric acid and nitric acid, and that's one of the few things that dissolves gold. So it dissolved it, and then he literally just put it in an Erlenmeyer flask, put a lid on it, and put an anonymous label on it, and then set it up top on a shelf. The Nazis came in, they ransacked his lab, tried to find stuff, but this Erlenmeyer flask just sat there, was never touched. When he came back, it was still sitting in his stockroom. He reconstituted the gold and then took it back to Sweden, and they reminted him his Nobel Prize. So it was kind of funny, little side note. So another side note with this is talking about Heisenberg and Heisenberg's something called the uncertainty principle. Many of you probably know Heisenberg from the Breaking Bad show that the main character took that name. I've only seen part of the first season, so I can't talk to that if anybody wants to ask me about it. Most of that is 100% true as far as the chemistry goes. All the rest of it, got no idea. So Heisenberg's uncertainty principle is the idea that our ability to look at something that's of the atomic size is not possible. And so what he actually states is that knowing the position and momentum of a subatomic particle at the same time is impossible. So my best analogy for this is if somebody takes a photograph of you using a flash, the light hits you, reflects off of you, and goes back to the sensor on the camera, and that information, in this case light, is stored in the sensor, and then it's turned into a pixelated photograph. The pixels are really close together, so it doesn't look like a pixelated photograph, but it is. So what Heisenberg is saying is atoms that are things that are the size of atoms, protons, neutrons, electrons, and whatnot, when you hit them with that flash, the flash itself actually moves the atom. So imagine somebody takes a photograph of you using a flash, and when the flash hits you, it slams you up against the wall and makes you bounce around the room. Obviously, that's not going to happen because you are massive compared to the energy of the flash of that light. But an atom is not. If it's going to absorb that energy is actually going to make it move. So basically, you're kicking it with light. So when you go to get the image, well, what the image is the light being reflected back. The light isn't being reflected back. The light was absorbed, and then the thing moved. So it's no longer in the frame, and there isn't anything reflecting back to you to see it. So if you've ever seen something claiming this is what a carbon atom looks like, or this is what the benzene molecule looks like, those are not actual photographs of those substances because you can't photograph them. Unless some other kind of technology occurs, we will never actually be able to see those atoms and subatomic particles. Okay. All right, so what we want to do now is this idea that we have these clouds of where the electrons are going to be located. We're going to get really specific. Heisenberg got really specific about what he's going to call these electrons, the positions of these electrons. And he's made it clear that two electrons can't occupy the same space. So in the same way that you and your best friend cannot stand in exactly the same place at the same time, somebody has to move. The same situation with the electrons. The electrons can occupy a space. And so in the same way that you have an address, like a state, city, street, number, and you can get more specific about what room you sleep in the house, what side of the bed you sleep in. So that's what we're going to do. We have 4 modifying factors that will determine the position of each electron, and that's going to be independent of all the rest of the electrons in that atom. So it'll be a unique feature. And so the things that we're going to be talking about with this are these terms that we're going to talk about are going to be level and sublevel and orbital and spin. And this is about quantum mechanics. We've had a little bit of discussion about that, but quantum mechanics basically is a discussion about how everything comes in pieces. It's not continuous. And we'll have a longer discussion about that a little bit later in this this topic about electrons. But for our purposes, there are no ramps. There are only stairs. That's the best way to put it. So nothing is ramped in the subatomic world. Everything has to be taken in pieces. I can't just move up an infinitesimally small amount. I have to move up a specific amount. When you're taking the stairs, you have to take a specific size step or increments of a specific size step. When you're taking a ramp, you could take as small a step as you want. So that's not the way it is with quantum mechanics. And so we're going to be dealing with these terms, and they're going to be based off of the quantum numbers that Heisenberg used to come up with his model of the atom. Heisenberg wasn't the person who came up with the quantum number idea or the quantum idea, that was another German, and that's named Max Planck. There's an institute in Germany named after him, the Planck Institute, and it is where a lot of Europeans go for higher level science learning and research. Okay, so again, these quantum numbers are going to end up being sort of an address for each one of the electrons. So we're going to start with the biggest one. This would be like the state that you live in. In this case, it's going to be the principal quantum number. And this is probably going to be confusing and convoluted until I associate it with the periodic table. And once that happens, you'll be like, oh, this isn't actually very hard. So I'm not going to say principal quantum number very often. I'm going to use the shorter term, which is just called energy level. And there are 7 energy levels, and all of the electrons will be housed inside of one of these 7 energy levels. So in the same way that you could say you live in one of the 50 states, you live in one of these energy levels as an electron. And in this case, there are 7 of them. Now, if you pull a periodic table out, so this tiny little periodic table, there are 7 rows on the periodic table. So how do you know how many energy levels there are? Because there's 7 rows on the periodic table. That's how you know. The next one is called, the principal quantum numbers symbol is a lowercase n. The angular momentum quantum number, these things are going to be called sublevels. I'm probably not going to say angular momentum quantum number after that last statement of it, and we're just going to say that those are sublevels. So we've got levels, and inside of the levels, there are sublevels in the same way that inside of states, we have cities. So the sublevel takes the energy level and divides it up into these sublevels, as it sounds like. The energy levels are different in their actual physical size. So depending on which energy level you are in, you have different numbers of sublevels. And it's really easy to remember how many sublevels there are in a given energy level because it's its number. So if I'm talking about energy level 1, then I'm talking about it only has 1 sublevel. If I'm talking about energy level 2, there are 2 sublevels. If I'm talking about energy level 3, there are 3 sublevels. And if I'm talking about energy level 7, there are 7 sublevels. The numbering for this starts with 0 and works its way up to, it's actually 6, and that gets us to 7 total, 0, 1, 2, 3, 4, 5, 6. There are letter designations for these sublevels, and the letter designations are S, P, D, F, G, H, and I. We aren't really going to talk about G, H, or I. G, H, or I aren't really going to be important to us because we don't have so many electrons that we actually need to use G, H, or I as a spot for them to be. So let me pull up another image here. Let's see. All right, so there's a building in Chicago. It's the tallest building in the country, regardless of what they say about the Freedom Tower in New York. The Willis Tower is actually taller. New tab. Here's the Willis Tower, and the Willis Tower is the tower that was in Ferris Bueller's Day Off, if you've seen that. Again, dating myself. This thing is 108 stories. And it holds, I forget, like 15,000 people or something crazy like that. It used to be called the Sears Tower, but Sears isn't around anymore, so they sold it off to whomever Willis is. Anyway, so you can fit, let's say the number is 15,000 people. So let's say that we took this tower and we moved it to the Port of Hood River, and dropped it right there on lot 1, which is that right now giant parking lot there in front of the event site, between the event site and 84. And everybody in Hood River had to live in this thing. Well, what would happen? Well, you could fit all of Hood River in this. Half the building would be filled. All right, well, what are we going to do with the top floors? Nothing. I don't have any reason to use the top floors, so we don't use the top floors. I'll use this analogy a little bit more and say that let's say that the elevator is broken. So what's the most important floor in this building? What is the most sought after floor in this 108 floor building? It's floor number one, the ground floor. So you don't have to take the stairs. Nobody's going to purposefully be walking up 108 flights of stairs to get to, and then down 108 flights of stairs to get down from your apartment. So the most important space is closest to the ground. And that's the way it works for an atom. The most important spaces are closest to the ground. Those are the ones that fill up first. Okay, so we've the reason that GH and I are not going to be used is because the biggest atom we know of is element 118. And if I use 118 electrons, I have still not filled any electrons into the G, H, or I sublevel. So we're just going to worry about SPDF and go with that. Alrighty. So is there a way to relate this to the periodic table? Yeah. Each one of the sublevels is going to hold 2 electrons. Each orbital holds 2 electrons. You know what? Let me back this up for a second. We're going to move on and then back up. So we've got energy levels, which is like the state. We've got sublevels, which is like the city. And then we've got the magnetic quantum number, or orbitals. And we're going to consider that to be like the street that you live on. All right. And so in these orbitals, I can put 2 electrons in each one of these orbitals. All righty. So what I'm going to do is I'm going to find my periodic table, and so I got this periodic table here. Maybe I'll just use a regular one. So here's energy level 1, row number 1. And this energy level 1 has 2 spots in it. I'm going to turn this into an image. So here we are with energy level 1. Energy level 1 has 1 sublevel in it. It's sublevel S. Sublevel S has 1 orbital. How do I know that? Because each orbital holds 2 electrons, and this is 2 atoms wide. 1, 2. Okay. So what about energy level 2? So again, this is energy level 1. Energy level 2 has an S and a P sublevel. This one has 1 orbital. This one has 3 orbitals. And that's how it works. So if I look at the energy levels, sublevel S has 1 orbital. Sublevel P has 3 sublevels. Sublevel D has 5, and sublevel F has 7. So it goes up by odd numbers. So if each orbital can hold 2 electrons, that means energy level 1 can hold 2 electrons. This energy level 2 has 2 electrons in the S sublevel, and it has 6 electrons in the P sublevel. Okay, so in energy level 2, I can house a maximum, a full amount of 8 total electrons. So how am I going to understand that on the periodic table? 1, 2, 3, 4, 5, 6, 7, 8. Energy level 2 holds 8 electrons. Okay, and that's how we're going to use the table to understand or remember how many electrons are in each of these. Okay. The last part, we'll just talk about it now, but we're going to talk about it in depth a little bit later, and that's going to be the spin quantum number. So this would be the number on the street that you live in. So your spin values are either -1/2 or +1/2, and that's the direction in which the electron's spinning. So all electrons are charged particles that are spinning, and they're either spinning clockwise or they're spinning counterclockwise. And in chemistry, they say spinning up or spinning down because they talk about the direction of the magnetic field that's associated with a charged particle that's spinning. All right, so I want us to, let's step through this. All right, so we've got blocks. We're going to divide the periodic table up into blocks. So here are the blocks that I'm going to divide the table up into. So this is the S block. And why is this the S block? Because it's too wide. This actually should be over here. It's not because of chemical reactivity reasons, but 2 electrons in each of these. So the S block has 1 orbital in it. So 1 orbital means 2 electrons. So this is 2 electrons wide. The P block is 6 wide. And because it's 6 wide, that means I must have 3 orbitals because each orbital holds 2 electrons. So that's 6 wide. The D block is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so that means that there are 5 orbitals. Remember, it's S, P, D, F, and it goes 1, 3, 5, 7. It's going up by, this is the number of orbitals. It's going up by odd numbers. And then my F block, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So there we go, 7 orbitals. And that means I've got 14 electrons since each orbital can hold 2 electrons. And so this is how we're going to use the periodic table to determine where we're going to find the electrons. They're in the S block, they're in the P block, they're in the D block, or they're in the F block. And the most important part about the atom is where the electrons end, meaning where that last electron is, because that's going to dictate what kind of chemistry that atom is going to be able to perform. This is actually what the periodic table is supposed to look like. It does not look like this because it would be too wide. So if you look on your periodic table, go down and find element number 56, which is barium, and element number 88, which is radium, and then go to your right. There's a hole there. And then it jumps over to goes from 56 to 72 and 88 to 104. Where are those missing elements? Go down below and you can find element number 57, and then right below it, element number 89. They've simply been pulled out of the periodic table. There is nothing else to it, simply to make it less wide. The person who did this, his name is Glenn Seaborg. He was writing chemistry textbooks, and he showed up at a conference and said, I'm doing this. And I'm doing it because my eyesight's going and I need to have larger fonts. So if you find a chemistry textbook from the 50s, you might see this version of the periodic table on the inside cover with a very small font. If you're looking at the table, you can also see that element number 107 is borium. So that's that Niels Bohr guy. He got an element named after him as well as his Nobel Prize. All right. The last thing I want you to remember from this set of notes are shapes of the orbitals. So the S orbital is just a sphere. It's exactly what we would expect it to look like. If I was wondering about where things were floating around a central atom, a central position, then I would expect it to be a sphere. So that's why it's not a circle, it's a sphere. That's why it has X, Y, and Z, because it goes up and down and left and right and front and back. So those electrons can be, if I've got my 2 electrons and they're in my S orbital, they're going to be inside of that sphere. So if I filled up my S orbital and I moved on to my P sublevel, then I've got 3 orbitals to deal with. And the orbitals are horizontal, like X on the XY axis, and then there's a vertical one on the Y axis, and then there's one on the Z axis. Each one of these is an orbital. And so since each one is an orbital, each one of these can hold 2 electrons, 2 electrons, 2 electrons. This S can hold 2 electrons, and that's it. If I try to put a 3rd electron in there, it gets pushed out because the electrons are negatively charged, and so they repel each other. So this is all of the p orbitals combined, and so this is 3 orbitals all together. So that means you could potentially put 6 electrons inside this object. I only care that you remember what the s orbitals and the p orbitals look like. I'm going to show you the d's and the f, but again, I don't care. The d's and the f's get, well, I would just say a little ludicrous. So there are, again, we've got 1 s orbital and then 3 p orbitals and then 5 d orbitals and then 7 f orbitals. It goes up by odd numbers. If we were talking about g, then we'd be at 9, h, we'd be at 11, and I, we'd be at 13. But again, we're not talking about those 3. So each one of these is an orbital. So I could put 2 electrons in here and 2 in here and 2 in here and 2 in here and 2 in here. And they're weird. And again, this is the math that Heisenberg came up with. And you could possibly see why coming up with this shape is going to be, the math for this is going to be hard. If you thought geometry and trigonometry were fun, this 3-dimensional math for shapes is not as easy. It's gonna take some work, or you're gonna just have to be able to see it spatially. So this is what they look like, and you can fit 2 electrons in each of those. Again, I don't care that you know what they look like. And then here are the Fs. They get even crazier. So there's a double donut ring here, and then we get these lobes that are in different orientations with themselves. Again, each one of these is an orbital. Each one of these holds 2 electrons. Again, I do not care that you remember these shapes. I only care that you remember that the shapes of the S is a sphere, and the 3 Ps are basically like dumbbelly or teardrop shapes that are connected to each other. And they end up forming this, I don't know, crazy balloon animal thing here. All right, and that's all I've got for you for this, this first lecture for electrons.